Imagine for a moment that you're sitting on a train traveling at 300 kilometers per hour. Outside your window, you see another train traveling alongside yours at the exact same speed. To you, it might seem as if the other train isn't moving at all, even though someone standing on the ground would clearly see both trains speeding by. Now, extend this idea further. What if, instead of trains, we're talking about light itself, the fastest thing in the universe? What if I told you that depending on your perspective, time slows down, distances shrink, and energy turns into mass? This is the profound and mysterious world of Einstein's theory of relativity, a set of ideas that changed physics forever. How did Einstein arrive at such radical conclusions? And why do they matter for our understanding of reality? Let's dive deep into this fascinating journey. The spark of genius, a young Einstein in 1905. Albert Einstein wasn't always a celebrated genius. In fact, in 1905, he was a young patent clerk in Bern, Switzerland, working on other people's inventions while pursuing physics in his spare time. But his imagination was boundless. One thought experiment, in particular, consumed him. What would it be like to ride alongside a beam of light? For centuries, scientists believed that light, like sound, must travel through some kind of medium, called the ether. But experiments, most famously the Michelson-Morley experiment, had failed to detect this ether. This left a profound puzzle. If light doesn't need a medium, then how does it behave? Einstein's insight was simple yet groundbreaking. The speed of light is constant for everyone, regardless of how fast you're moving. This realization turned physics upside down. Special relativity, time, space, and energy reimagined. In his 1905 paper, Einstein introduced the special theory of relativity, which applies to objects moving at constant speeds. Its foundation lies in two postulates. 1. The laws of physics are the same for all observers in uniform motion. 2. The speed of light in a vacuum is always the same, no matter the observer's motion. But these principles had profound consequences. If light's speed is constant, then time and space themselves must be flexible. Let's explore three key outcomes. 1. Time dilation, when time slows down. Imagine you're in a spaceship traveling close to the speed of light. Inside, you feel normal, your heart beats, your clock ticks, and life proceeds as usual. But to someone watching from Earth, everything on your spaceship appears to slow down. This phenomenon, called time dilation, means that time moves differently for observers in motion relative to one another. Experiments have confirmed this with astonishing precision. For instance, atomic clocks placed on high-speed jets tick slightly slower than those on the ground. Astronauts aboard the International Space Station experience time more slowly than people on Earth due to their high orbital speed, though the difference is tiny. This effect is no mere curiosity. It's critical for technologies like GPS, where satellites in orbit experience time dilation and gravitational effects that engineers must account for. 2. Length contraction, shrinking in motion. As objects approach the speed of light, they appear to compress in the direction of motion. This effect, called length contraction, is imperceptible at everyday speeds but becomes significant at high velocities. For example, if a spaceship were moving at 90% of the speed of light, it would appear squashed to an outside observer. From the perspective of the passengers inside, however, everything would feel normal. 3. E equals mc². Energy and mass are the same. Einstein's most famous equation, E equals mc², emerges naturally from special relativity. It tells us that energy, E, and mass, m, are interchangeable, connected by the speed of light squared, c², a colossal number. This simple equation explains why. Nuclear reactions, like those in stars, release immense energy by converting small amounts of mass. Particles accelerated to near light speeds in colliders gain enormous energy, increasing their effective mass. General relativity, gravity is the curvature of spacetime. While special relativity focused on objects moving at constant speeds, Einstein soon turned his attention to more complex scenarios involving acceleration and gravity. In 1915, after years of struggle, he unveiled the general theory of relativity, a masterpiece that redefined our understanding of gravity. Gravity, not a force, but a curve. Isaac Newton had described gravity as a force between masses, but Einstein offered a deeper explanation. Mass and energy warp the very fabric of spacetime, much like a heavy object placed on a trampoline. This curvature tells objects how to move. Planets orbit the Sun not because of an invisible pull, but because spacetime itself curves around the Sun, guiding the planet's paths. Astonishing predictions of general relativity. Einstein's theory wasn't just elegant. It made bold predictions that could be tested. Light bending around massive objects. In 1919, during a solar eclipse, astronomers observed starlight bending around the Sun, confirming Einstein's theory. This phenomenon, known as gravitational lensing, is now routinely observed in astronomy. Gravitational waves, when massive objects like black holes collide, they send ripples through space-time, like waves spreading across a pond. In 2015, scientists detected these waves for the first time using the LIGO observatory, a discovery hailed as one of the greatest in modern science. Time runs slower in strong gravity. Near massive objects, time itself slows down. This effect, called gravitational time dilation, has been confirmed with experiments involving clocks on mountains and satellites. Black holes, perhaps the most mind-bending prediction. Black holes are regions where space-time curves so steeply that not even light can escape. Modern telescopes have captured stunning images of black hole shadows, directly validating Einstein's equations. Everyday applications, relativity in your pocket. You might think relativity only matters to astrophysicists, but it plays a vital role in your daily life. GPS technology. Satellites orbit Earth at high speeds and weaker gravitational fields, causing their clocks to tick differently from those on the ground. Engineers use Einstein's equations to correct these discrepancies, ensuring your navigation apps work accurately. Medical advances. PET scans, used in hospitals, rely on the principles of E equals mc² to detect energy emitted by particles. Philosophical impacts, shattering old certainties. The theory of relativity didn't just transform physics, it revolutionized how we think about reality. Einstein showed that time isn't universal, it's relative to your frame of reference. Space isn't a passive backdrop, it's dynamic and flexible. Mass and energy are two sides of the same coin. This new worldview was unsettling, yet profoundly liberating. It revealed a universe more interconnected and mysterious than we ever imagined. The road ahead, relativity meets the quantum world. While relativity explains the cosmos on large scales, it struggles to describe the subatomic world, governed by quantum mechanics. Reconciling these two pillars of modern physics is one of science's greatest challenges. Could Einstein's legacy guide us toward a unified theory of everything? Or will the next great breakthrough come from someone inspired by his questions? The theory of relativity isn't just about equations or abstract ideas, it's a testament to the power of human curiosity. It shows us that by daring to question the familiar, we can uncover hidden truths about the universe. So, the next time you gaze at the stars, remember, time, space, and reality itself are more wondrous than they seem. Are you ready to ask the next big question?